Swayam Prabha. Digital India. Educated India.
Good morning. So far we have discussed some common features of mass transfer operations with regard to material balance and various methods of conducting mass transfer operations, co-current, counter-current, so on so. Also we discussed about equilibrium line, material balance line, as well as the driving force line, and the combination of these three will manifest in the design of mass transfer operating equipments. Now we will go specifically to certain mass transfer operations. I will be starting about absorption. So we will discuss about absorption and stripping, which are basically similar kind of processes. It's just a matter of the direction of solute transfer. So in absorption, it's basically a gas liquid operation, and a solute A diffuses from a gas to a liquid. Okay, this is what we call as absorption, whereas in the stripping or desorption is also gas liquid, but here the solute A diffuses from a liquid to a gas. Okay, so only the direction is different in these two operations. Now, from an industrial point of view, chemical industrial point of view, what are the type of gases that we would like to purify or clean? So we have a set of industrial gases that we need to remove. For example, so you can see that looking at this variety of manufacturing process, for example, in case of ammonia manufacturing, the gases to be removed would be carbon dioxide, ammonia, and H2S. So these are some of the polluting gases that we want to remove before the fluent gas or the effluent is actually discharged to the environment. And if you look at coal gases, high bitumen or low bitumen gases, again we have carbon dioxide, H2S, and in the case of desulfurization we have SO2. So predominantly we are talking about ammonia removal or SO2 or CO2 or H2S. So predominantly these are the gases that we would like to remove from an effluent gas, and in this case you have a kind of a range of concentrations in these flue gases that we would like to remove. So you can see that ranges from 1 ppm to several hundreds of ppm, okay, and these are beyond the threshold of safe discharge. So we need to remove them before it can be discharged into the environment. Okay, so this is the context that we are looking at, how to separate these harmful gases from the effluent is the problem of absorption. Okay, so this is what the solute I mean. Okay, this will be a solute in a background gas. It can be air, or it can be some other inert gases from which we have to remove this set of gases. So as I said, it's a gas liquid operation. We would like to remove these solutes into a liquid. Okay, we want to transfer the solute into a liquid. Then the liquid is basically, we call them as solvents, and the choice of solvent also involves different decision making. For example, there are solvents which can absorb the solute purely from a physical means. Okay, what I mean by physical means, the gas simply dissolves in a liquid. Okay, for example, carbon dioxide absorbing in water. Okay, sometimes we have a a solvent which can chemically absorb, which can react and then absorb into the liquid. Okay. So, we have to choose between which solvent are physical and which solvents are chemically oriented. Okay. So, general choice is that if the mole fraction of the solute in the gas phase is more than 10%, okay, if it is more than 10 mole percent, we would like to actually go to physical solvents. Basically, the the solute is basically just dissolved in a physical solvent. When this mole fraction is very small, we would like to use chemical solvents, where the absorption will also involve a reaction with the solute and the solvent. To give an example, if I take let us say I want to think about H2S removal, okay, hydrogen sulfide removal, and for the physical solvent the choices can be ethylene glycol. Ethylene glycol is a physical solvent, or propylene carbonate. Okay, these are examples of physical solvent. Whereas, if you want to do chemically, the chemical solvent examples can be monoethanolamine or NaOH aqueous solution. Okay. So, these solvents will chemically absorb the gas H2S, whereas these physical solvents will simply dissolve the gas into the liquid. Okay. And in general, when we think about a solvent for absorption, we have to think about a solvent that has high solubility. Solubility should be high, and we want them to be less volatile. So, volatility should be very less. So, what will happen if it is more volatile? If the solvent is more volatile, what does it mean? Yes, it will go to, so apart from the solute, the liquid, the solvent will also getting exchanged into the gas phase. So, then you are talking about multi-component absorption desorption issues. Okay. So, we want to have the solvent to be as non-volatile as possible. Okay. So, it should not have high vapor pressures. Okay. So, the volatility should be less, and sometimes the solvent can also be very corrosive. Okay. And we want them to be less corrosive. Okay. Given a choice of solvents, you have to always choose the one that has less corrosive property. Of course, cost should be always cheaper. Okay. So, cost should be as low as possible. There are other conditions like viscosity, you want them to be as low as possible. So, what will happen if the viscosity is very high? Yes. So, viscosity high means the power required to pump it, the pressure drop involved will also go up. So, we want to have as low viscous as possible. Toxicity, we want a solvent with more toxicity or less toxicity? Very less toxicity, of course, okay, for safety purposes. So, these are a very general rule of guidelines that we have to follow in the selection of solvents. Now, we will talk about absorption equipment. So, I have been so far generally talking about mass transfer operation equipment in a very general term, but now as we go to specific mass transfer operations, then we will be talking about specific mass transfer equipment also. So, for the industrial scale absorption, generally we use what is called a packed column, okay, or a packed tower. So, it looks something like this. So, a packed column is nothing but a cylindrical vessel, and it has a packing of some inert material, okay. And typically what happens is the gas enters from the bottom and then leaves at the top, and you can see there is a small grate here that allows distribution of the gas into bubbles. Whereas on the top a liquid comes in, there is a liquid distributor sprinkling the water in the packing above, and then the liquid basically collected as a pool here and then drawn out. Okay. So, this is the liquid distributor that you can see small nozzles over there, and this entire bed is a bed of packing, and this packing is used because we have to have a good contact between the incoming gas as well as the liquid. Okay. So, the liquid and gas will actually wet around the surface of this packing material and then pass each other. Okay. It is a counter current flow, gas is entering from the bottom, leaving at the top, and liquid is sprinkled at the top and then leaves at the bottom. You can see that you can also have an intermediate liquid distributor to collect and redistribute the liquid again. Okay. If the column is so high, we may have multiple liquid distributor placed in between also. So, if you look at the packing material itself, if you look into this packing material, there are different kinds of packing that is used in industry. So, we have something called as simple as a Raschig ring. Okay. A Raschig ring is nothing but a hollow cylinder. It looks like a small hollow cylinder. Okay. So, the size can be between 6 millimeter to hundreds of millimeters. Okay. And then there is something called this burl saddles, which has a saddle like shape, and then interlocks saddles, pal rings, high pack ring, and nutter ring. So, these are all typical packing materials used in this kind of packing, and the material that are used to make these packing material could be metallic, ceramic, or sometimes plastics also. Okay. And this packing can also be very randomly packed. So, you just basically dump all the packing material to a particular height, or you can also have more structured packing. Okay. So, what I have shown here is actually a random packing, but you can see there is an example of structured packing, meaning that the packing material is not arranged randomly, but it is placed in a particular sequence of order. Okay. So, you can see in this case the Raschig ring is actually arranged nicely as layer by layer. Okay. So, what you are seeing here is a top view of these units packed in various arrays of these rings over and over. Okay. So, that water and gas can go through a well defined paths, whereas in a random packing the gas and liquid will go through a tortuous paths. And you can see that sometimes you have this kind of logs which are aligned perpendicular to each other. So, these are some examples of structured packing, and then there are also random packing. These are the things to remember. Now, in the context of design, okay, so what we are asking is, we are asking two questions. One is, what should be the diameter of this column, and what should be the height of this packing? Okay, these are the two questions we would like to answer. Okay. So, and these two are kind of a little bit independent choice. We make the calculation of the diameter based on the pressure drop calculations, whereas the height we calculate based on the mass transfer rates. So, what I will do now is, I will first talk about the fluid mechanics of packed bed, which allows us to calculate the tower diameter. Later on, we will move to mass transfer rates to calculate the height of the tower. So, generally when we look at flow through packed bed, generally we have a packing and then a single fluid is going from one side to the other. Okay. So, this is known as flow through packed beds. Flow through packed bed, and a famous equation known as Ergun equation is used to calculate the pressure drop in such a situation. Okay. It goes something like delta P by Z Gc epsilon cube dP rho g over 1 minus epsilon So, this is the famous Ergun equation that is used to calculate pressure drop in a packed bed. So, delta P is the pressure drop, Z is the length of the packed bed, and epsilon here is the porosity, dP is the diameter of the packing material, and rho g is the density of the gas. This g prime here is the gas velocity, gas flow rate, okay, or the fluid flow rate. On the right hand side you have two terms. This term is dominant when you have a laminar flow, and this term is used for turbulent flow. So in that way, Ergun equation is actually applicable for both laminar flow as well as turbulent flow, but one of the term will be more dominant if you have a specific flow like turbulent or laminar flow. So now this is only applicable if you have a single fluid flowing through a packet bed. But if you look at the packet column used for absorption, I said there are two fluids going in opposite directions. Okay, so that has to be a little bit more complicated than Ergun equation. So this particular diagram kind of illustrates schematically how the pressure drop is developed when you have a flow through a packed column in which both gas and liquid are flowing through a fixed bed height. So you can see that delta P is plotted, delta P by Z, that is a pressure drop per unit length of packing, is plotted against the logarithmic of the gas velocity. Okay, I'll talk about what is this gas mass velocity in a moment, but it is basically flow rate of your gas phase or a fluid phase in this case. So if there is no liquid flowing in, okay, then it's basically a simple Ergun equation kind of a situation, and you can see this line will have a slope of 2, because as per the Ergun's equation I said that in the case of turbulent flow you can see this delta P by Z will be proportional to G square, G prime square. Okay, so that is a case of no liquid flowing, only gas is flowing. Okay, so that's a flow through a packet bed with a single fluid flowing in. So that would be the straight line that you see here. Okay, this is called dry packing, no liquid, only gas. Now let's say you would turn the liquid on from the top, and these curves corresponds to different flow rates of liquid. So starting from 5,000 units, 10,000 units, 15,000, 20,000 units. Okay, and if you go from, suppose if you look at this vertical line, let's say you fix the flow rate of gas and you go from one curve to the other curve, meaning that you are going from no liquid to a particular liquid, 5,000 units of liquid flow rate, and then 10,000. What you see is that as the flow rate of liquid increases, the pressure drop also increases drastically. Okay, but this is very intuitive, because when you have gas flowing in and it will be flowing through all the pores, void volumes, void paths. The moment you put the liquid from the top, the liquid will also occupy certain space, certain pore volumes. That means the fluid will have lesser and lesser pore volume to flow through, and obviously this will lead to increase in pressure drop. So if you keep on increasing the liquid flow rate for a given gas flow rate, the pressure drop will keep increasing. Okay, so that's what this nature of these curves are. So you can fix one particular gas velocity and you can keep on increasing the liquid velocity, and you will see delta P will increase. Okay. Secondly, if you look at these curves, you can see the curves are going leftwards. If you increase the liquid flow rate, and you can see the pressure drop also increases. Okay, if you see these curves are moving to the left, meaning that even at low flow rates of gas itself, the pressure drop will start increasing the moment you have higher flow rates of liquid. Now the important thing to note here is, you will see that at some point of time the liquid will not be able to come below, it will get accumulated in the packing itself. This is called loading. Okay, the liquid holdup will start increasing because the gas is pushing upward and the liquid is not able to come down. Okay, and if you keep on increasing even beyond, what will happen is something called flooding. The liquid will get pushed out of the tower itself, because there's no way they can come down. So these are the operating issues. So you don't want to have gas and liquid velocities that corresponds to flooding conditions, and you typically operate around the line A and below. Okay, just about loading. Okay, that's the kind of practical or optimal operating flow rates. Okay, so for every given packing, we should study the flow rates and then decide what sort of liquid and gas flow rates we should be using for the packing. Now we'll move to something more practical about this in way of calculating the pressure drop in these columns. So generally what happens is that you will have curves like this for pressure drops. Okay, so these are set of curves, but it's actually what I showed here is a little bit more intuitive. We are talking about so in these plots I showed increasing the gas flow rate for a fixed flow rates of liquid and the resulting pressure drop. This is more intuitive, but then in practical terms, in literature, these pressure drop curves are plotted slightly differently, okay, in a different sort of units. So this plot and the one I am showing below are essentially the same thing, but only thing is we have changed the x-axis and y-axis in some other units. Okay, let me also explain what that means. So you can see that I am showing two plots. One is for a random packing, where the packing material is randomly packed throughout the absorption column, and correspondingly this is the plot for the pressure drop in a random packing. The one below is for structured packing, where the packing material is arranged in a particular sequence in a particular order, so that the packing itself is a little bit systematic. Okay, so I was trying to say that the even though the pressure drop curves are shown schematically in this particular plot, where pressure drop is plotted as a function of gas flow rate for a given set of liquid flow rates, but in the literature, in handbooks, you will see the pressure drops reported in slightly different unit systems. So here the x-axis here, the abscissa, is actually in terms of, so we have L dash by G dash. This is the flow rates of liquid versus gas flow rate ratios multiplied by the square root of the density of the gas over the density of liquid. Okay, so that's what this x-axis means here. Okay, and the y-axis is called a capacity factor. So this is in short we can use a CF. This is defined as G double prime F 0.5 nu 0.05 over square root of rho G into rho L minus rho G. This entire term is actually denoted as a capacity factor, and that's what is used in this y-axis here. Okay, and you can see that each of this curve here now corresponds to different pressure drops. Okay, and the pressure drops are given now in the delta P is given in the units of inches of H2O over feet of packing. So in other words, generally in the we are basically looking at this kind of a pressure drop versus flow rate scenario like this, like pressure drop as a function of liquid and gas flow rates, but instead of that the plots are made for a given pressure drop, what are the possible flow rates. Okay, so the information is actually replotted differently. So generally the way we should use this curves is that we will first calculate the capacity factor as well as this ratios of the mass velocity, and then see in which curve this that point actually lies, and then the corresponding pressure drop will be calculated. In other words, we can even sometimes say that I want to have a particular pressure drop, that's a design pressure drop. Correspondingly, we can see how much is the flow rates of the gas and liquid. Okay, so that's the way that we should use this particular plots. The one catch in using this plot is that all the units used in this particular plot are in English units. Okay, mostly we use SI unit for other problems, but in this particular pressure drop calculation, these plots are available only in English units. Loading and flooding. So, so as I said that when you have, let's say you have a fixed gas flow rate, and then you start turning the liquid. Okay, so when the liquid flow rate is very small, and liquid will trickle down, flow through and then leave. Okay, so that's a safe operation. And let's say you want to absorb more of the solute by increasing the flow rate of liquid. Okay, so when you turn the liquid flow rate more and more, what will happen is at some point of time the incoming gas will not let the liquid down, and the liquid will start accumulating. Okay, and this accumulating liquid will also increase the pressure drop. You can see the change in the slope of these lines. Okay, so you can see in the first phase, so you see that suppose if you take any of this line, you see that the slope is at a constant, it's increasing at a constant value, and then suddenly you see that this change is the slope is a little changing here. Okay, you see there's a little bit of change. So that is the signature of the liquid getting accumulated in the column. That's what I call loading. Loading means the volume fraction of liquid starts increasing. Okay, and if you keep on, so suppose if I take this particular, let's take this particular flow rate. Okay, 15,000. And what you're doing is you're fixing the flow rate of the liquid, and you're systematically increasing the gas flow rate. Okay, so you see initially the pressure drop increasing pretty much constantly here, and then if you keep on increasing the gas more and more, at some point of time the liquid will start accumulating, because the incoming gas is actually pushing the liquid up, not letting them down. And remember, the liquid is only coming because of gravitational force, and you see there is a change in the slope. Okay, so this change in the slope is actually an indication that the liquid is getting accumulated. Okay, and then if you keep on increasing the gas flow rate, at some point of time liquid can only be held up only up to a particular packing length. Beyond that, the liquid will actually start overflowing from the top of the column. That's what we call as a flooding. Flooding basically means water coming out of the column. Okay, and that is, so this is important because in deciding what should be the flow rates of the gas and liquid, what is the allowed pressure drop, we have to systematically optimize it. Okay, so generally operating under flooding condition is not permitted, because absorption will not happen, and it is not a safe operation also. If you do it below the line A, you are basically operating the column under underperformance. Okay, the optimal performance somewhere between A and B, where you are not letting the column to flood, at the same time you are able to operate at highest possible gas and liquid flow rates. Okay, so the design, in terms of design, generally we say that the delta P by Z should be just about flooding pressure. Okay, so suppose if I take the line B here, that is the pressure drop corresponding to flooding, and you have to operate always below that pressure drop. Generally the design specification will be operate the column at 80% of the flooding pressure drop. So what you do, you first find out what is the pressure drop corresponding to flooding. To that you make 80% of the pressure drop. That line will be somewhere here maybe. Okay, and then you choose, you decide one particular liquid flow rate, correspondingly calculate the gas flow rate, or vice versa. You decide the gas flow rate and then find out the liquid flow rate, so that you are always below that flooding line. I will have couple of numerical problems I want to do, but because of time I could not do it. But in the next class I will show how to use this. There are only two challenges. One is you have to convert the units into English units to use these plots, and second is this calculation of flooding pressure drop, and then accordingly calculating the flow rates of the mass gas and liquid, and from there we will calculate the diameter of the column. Okay, so fluid mechanics comes only in deciding the diameter of the column. Okay, so